Okay, so hi everyone. Thanks for coming today. Today we have an excellent speaker, Ondrej Hulik, from the Central European Institute of, I forget the acronym, CEICO. And he's giving a talk today on some of his work related to T and U dualities. So take it away, Ondrej.
Thank you. Okay, thanks for inviting me and this opportunity to give a talk. I hope it's not too introductory, and that I'll get to some interesting stuff towards the end. And if you're welcome to stop me at any point and ask questions so that we can find some right pace to proceed. But okay, so you can see my screen, right? And hopefully my cursor also, like so that I can point on stuff. Is everything working?
Everything looks great.
Yeah. Okay. Good. All right. So I'll give a talk on some aspects of some geometric aspects of T and U duality, and so basically my talk will constitute of three parts. I'll first give some historical review or where T duality occurred in the first place, and then I'll explain this on an example of world sheet string and how we obtain various generalizations of T duality. Then I'll say something about mathematical structure of Drinfeld double, and then I'll move more towards right geometric description of these interesting symmetries, such as generalized geometry and exceptional geometry for Udality generalization. And then hopefully, if time permits, I'll conclude with some interesting questions we're trying to address with my collaborators. So, but let me start with basics, and that's the study of string theory from the world sheet perspective. So as we know, the string is two-dimensional object which moves in a target space, and just the fact that it's extended object rather than point-like object in normal QFT, it has this interesting set of dualities bound just to this fact that it's extended object, and the first manifestation of this happens when we study string moving in torus, just a simple target space, and it turns out that if one quantizes the string and looks at the spectrum, one notices that this is the spectrum of the string of the excitations, and one notices this peculiar fact that we can exchange momenta and windings of the string, because string is again an extended object, so it not only has momentum but winding modes, and this spectrum is is symmetric under swapping these two quantum numbers. But it's not just straightforward swapping. One needs to also accompany it with change of these constants. So R is a radius of one of the circles of the torus, and if one switches that for 1 over R and with alpha prime with the constant, then one has the same spectrum, and this led people to interesting realization that it seems as though the string moving in a circle with the radius R gives the same spectrum as if it was moving in the background with the radius 1 over R. This is the simplest manifestation of T duality. And obviously this led to interesting research as to how we can generalize these ideas further.
I have a question. You have the action at the beginning, but you don't define what is G, B.
Oh, okay. Yeah, sorry. So string, as we usually define it in Navier-Schwarz formulation, couples to fields of supergravity in the background. So G is a metric in the target space, and B is a B field, NSNS B field, which is some two-form describe, constituting some degrees of freedom of supergravity. I'll get more to supergravity and and full description of duality later on. But yeah, it couples naturally to part of supergravity fields in the target space.
Sorry, Ondrej, if I could just follow up briefly on that question. So G is a metric, but the action seems to have a wedge product there. Is this G is an anti-symmetric metric, or?
Is something.
Oh, but there's a star. Here's a Hodge star. So this first term is actually symmetric. The second one is two forms. So the one couples naturally to something. And
I see. Okay, thank you.
Yeah. But yeah, Hodge is on the world sheet. Yeah, it's kind of mixing of structures, right? This is a target metric, but this is a world sheet Hodge, and but it plays well together. One can write it maybe in more down to earth terms. I chose this more geometric and maybe more confusing way.
Oh, yeah, and one last question before you go to the second slide. The M and the U for the duality, what do those two variables represent in terms of the dynamics of the?
Oh, these ones?
Yeah.
Oh, they are quantum numbers. So if one quantizes the string, if you quantize particle, you know that there's just one quantum number, which is momentum. Yeah, and if your target was compact, you know there's a quantization of that number. So it's basically integer for every quantity of momentum. But if you have an extended object, there's also winding, which basically tells you how many times your string winds around compact cycles in target space. So you have these two quantum numbers, and they could be exchanged. And you see there's there's no this T-duality, this exchange of winding and momenta. It's by far not obvious symmetries. It's not like if you were searching for what symmetry is behind this degeneracy of the spectra, there's not like a rotation or translation in your target space. It's not that simple. It's really something deeper than that. And first people who studied this was probably the first paper was by Buscher, but then interesting generalization came from Rocek and Verlinde. And they realized this interesting fact that you can look at your Lagrangian or action for string, and if it admits a killing vector, then so this is my killing vector. You can now I can write killing vector. You can prescribe this this transformation for your X fields and look how action transforms. This will be the result. And it turns out that if you want your symmetry to be invariant under it, you need to kill these two terms. The simplest way to do it is by setting them to 0, meaning that your metric and B field in target space are invariant. And if that happens, you see your action is invariant under this killing vector. Those are really the directions in the simplest toroidal example. Those are the directions along the cycles of the torus. And this simplest relation of LG being 0, that would really tell you that your metric doesn't depend on that target space coordinate along the cycle in the torus. So you see that having this symmetry in your model is rather restrictive. It tells you that the metric is virtually constant along those cycles. So, but nevertheless, if you have this situation that those two terms are 0, you can gauge this symmetry. You can promote so before we had this epsilon, which was constant. You do the usual gauging. So the way you do that is by promoting these D's to covariant D's, which look like this. It's slightly non-trivial because people are usually used to having some X here, but since it's a shift symmetry rather than rotating by some matrix as we usually gauge in general relativity, it's really just shift by connection. And then we can add it to our action. We can just substitute this covariant D in our action, and by so doing, we gauge the symmetry. However, we need to supported by extra term, and that is gauge fixing term, so that we don't really change the degrees of freedom of our model. And if that's done by adding this term, this gauge fixing term. You can see that,
wait a
yes.
minute. Is it you are saying that it seems to me like your gauge is deep invariant of the action, right? Is this correct?
Sorry?
Is this the gauge symmetry here is a deep invariant of the action? Is this correct?
So
Or
so the action was invariant under global symmetry given that by a killing vector in target space. But by localizing it,
V is a killing vector, you mean?
yes, but in target space.
Okay.
And this is assumption. If it's symmetry of your action, you can do the gauging. It's more like a trick rather than something deep at this point.
Okay.
It really, it's just a way to obtain this dual model as we'll get forward. But just think of it as a dirty trick. And okay, so if we add this gauge fixing term, we can see that we had our action which depends only on x. If we add this gauge field and x tilde, we get some action up here, which we call parent action, and it's sort of equivalent to the original action. And the way to get it is to vary it with respect to x tilde, and which tells us that f is 0. Varying the action that gives us that f is 0, and meaning that a is pure gauge, and then we can subsume a in x and get our original action. However, if we switch this procedure and first gauge fix x to be 0 and then integrate out a, we get to a different action which we call dual action, and we obtain a equivalent model to the original one, from which if we read off the geometric data, if we look at what the G and B, new G and new B are, we get totally different geometry. So interestingly enough, this recovers the original manifestation of T-duality as I introduced in the first slide. So if you had just modeled with one-dimensional target and your metric, you had no B field and metric was just R, then you get 1 over R in the dual model. So indeed, you get the previous result. But in more general situation, on a toroidal compactification, it gives you these famous Boucher rules. So, sorry, was that a question?
Actually, can I ask real quick?
Sure.
Is there any assumption on kind of the algebra of killing vectors as abelian to start with? Or are you only focusing on kind of an abelian?
Oh, excellent question. And we'll get to it later. But so yeah, for now, yeah, that's a thing I didn't say. For now, the whole algebra of killing vectors is abelian, but we will relax that later on.
Great, thanks.
But for now, yeah. So if it's abelian, we call it abelian T-duality. That's a thing I should say probably. And so these Boucher rules, you can see that I've written just few of these rules how to get the G tilde as in the G in dual model, and B tilde is not here, so just G tilde in dual model from the original geometry. And you see those are horrible expressions. Those are just some nonlinear expressions in terms of metric and B fields from the original model. So it seems like a mess, but what comes as a total surprise, if you didn't know all the other theory, is that if you have started with G and B, which solved supergravity equations, this new dual non-linearly obtained geometry will also solve supergravity equations motion. So that's quite surprising fact at this point. And now one can wonder how one can use this simple dualization procedure and generalize it. So we'll look at two things now, and one is how to unclutter this mess of nonlinear transformations, how to write it in slightly better language, which leads us to generalized geometry. And second thing is following the question, what happens if we relax the fact that we're just gauging the 8 billion killing vectors, and what more we can do. So first, let me actually go to the second point here. And okay, so we can actually proceed in 3 steps in generalization of abelian T-duality. There are always 2 things which will be slowly relaxing. First, we had the abelian T-duality where the killing vectors were fully commuting. I wrote it as a Lie derivative, but this is obviously commutator as well. So we had this situation, and we required that Lie derivative of G and B is 0. We can relax the first assumption on commutativity, and then we call this. We can again gauge this. It will require to introduce non-commutative, non-abelian gauge field, but things can be done. There are some problems with that, but the procedure is called non-abelian T-duality. That's when we relax the first assumption, but we still keep the second assumption on having those target space metric and B field invariant under B. There's a third interesting relaxation on these assumptions, and that is that we will have a non-abelian symmetry we're gauging, but also we no longer have this LG being 0 and LB being 0. Instead, it will have a very special form, which is rather complicated in terms of G and B, and I won't write it here, but it can be written much more succinctly when we use instead Vielbein. So G is basically E squared, as we know from relativity. In quotation mark, there's some flat space metric, but if we assume that Vielbein, when taken Lie derivative with respect to other vector in the frame field, transforms in kind of Lie algebra prescribed way with different structure constants than we have here, then this situation is called Poisson-Lie T-duality, and we'll have more to say about it later. But it seems like in the most general situation so far, we have 2 structure constants entering in, and they are there's some relations among them. Okay, the last piece of information which kind of puts all these 3 examples on the same footing is a notion of Drinfeld double, which was introduced by Klimčík and Špera. It basically amounts to reinterpreting all these T-dualities in a following way. So instead of starting in one model and T-dualizing in a second one, we formulate an action we formulate this parent action first on some space. We call that Drinfeld double, and then by some projections down to certain subspaces, we obtain those T-dual models, and the data needed is called Drinfeld double. It really amounts to having a Lie group with split pairing, meaning that we have a pairing at the level of the algebra, which is split signature, and then these dual models are obtained from choosing 2 isotropic subgroups in our original Drinfeld double G. This is interesting because before it seemed like T-duality really started from one description, and then it led us up to the parent action, down to the T-dual description. But now if you start in parent action, you actually have a multitude of ways to find H and H tilde inside, different H and H tildes. And every time you choose these, there are some restrictions on them, but every time you get this pair, you get 2 T-dual descriptions. So you have whole plethora of T-dual descriptions within this one parent action. And this gives you plenty of interesting models within. So it subsumes those 3 interesting situations I described before, but it also fits in all these eta and lambda deformations in integrability theory and so on. But I won't get into that. Okay. There's so all I said was for strings, and in M theory, we have something called Udality, which is a generalization in M theory setup. I wrote this dictionary. So I said before that string naturally couples to supergravity degrees of freedom. If we start with M theory, we hope there's a brain description behind, much like string gives the basic degrees of freedom of supergravity. The degrees of freedom in supergravity were G and B, the metric and B field. Here it's metric, but 3 form. And this will get later into there's a nice geometric description in terms of generalized geometry. Here will be exceptional geometry. And most importantly, Drinfeld double will be replaced by some more interesting algebraic structure called Leibniz algebra. But first, I'll get to the generalized geometry part, which is the nice geometric description of T-duality and the previously described phenomena. Maybe I'll stop for questions if there's any. And if not, then I'll continue. Okay. So let me just say.
Well, I have a quick non-technical question. So I don't know that much about string theory and M theory, but do they give similar predictions for supergravity or for the gravitational, the graviton gravity fields, or are there like conceptual differences on the questions they're trying to answer?
So M theory is something. So first of all, M theory is at the level of supergravity. M theory is low energy effective. So supergravity is low energy effective action for string theory, right? The full description of the whole situation would be string field theory, which is second quantized string theory, but no one knows the full description of that. But we only, when we really care about the massless degrees of freedom, mostly we don't know what's the analog of string theory description. We just know that this low energy effective action is M theory. We know that it can have, it's not just described by string-like excitations, but the full description in terms of something like string theory is not known. There are attempts, but it's not by far complete. Okay, so generalized geometry, it's extension of the usual geometry, which allows us to incorporate all these interesting and unusual dualities in the usual geometric fashion as we like it. So it really stems from a simple idea of extending a tangent space. Usually the physics or everything we study happens in tangent space, and in geometric objects define on that, so like metric and vector fields and stuff like that. And in generalized geometry, the idea of this is that we replace tangent space by generalized tangent space, which we call by this double TM, and it's really just direct product of TM and T star M. It has a ODD structure on it, which means that in terms of G structures, we know that. Just a quick digression, that if we associate it to TM frame bundle, meaning a bundle of frames in every point, it has a natural GLN structure, meaning that we can rotate a frame in every point by GLN group. Here, however, there's a natural canonical structure on this bundle. Like if without defining extra structure, you always have this canonical pairing, which takes a vector and form and evaluates the form on a vector and gives you a number. So this is a natural canonical structure bound to this object, and that gives you ODD structure on a frame bundle. And then lots of geometric structures extend from the usual geometry. So normal we need Lie derivative and commutator, and that extends to something what's called Dorfman derivative and Courant bracket. I'll talk more about it later. There's a natural extension of G of metric, and we call it generalized metric. And in here it lives in maps of Tm to Tm. Clearly, if we started with d-dimensional space, this is d-dimensional, so 2D-dimensional metric matrix. It looks like this in some local coordinates, and you see that it's related to the previously defined geometric data G and B. So if you take these two objects describing a target space geometry and put them in this nonlinear fashion into this matrix and call it generalized metric, it comes as total surprise that those T dualities, as I described before, given by horrible nonlinear transformations, they just get this very simple form of conjugating the generalized metric by some prescribed matrices from left and right. So that's a nice simplification. At least it gives you so many examples. Just starting from one simple solution, you can just rotate by these ODD matrices. A is in ODD matrix group, sorry. And then if you read of G and B, you get some T-dual description. So it's a nice solution generating technique. Okay. So just quick note on how these Dorfman Lie derivatives or analogs of usual Lie derivative and commutator are defined. It really comes from the fact that the generalized geometry, it somehow geometrizes, it puts on the equal footing the infinitesimal diffeomorphisms and gauge transformations. So we know that the x in Tm, the section of Tm, it gives us infinitesimal diffeomorphisms and omega in sections of T star m. It could be, we can take a d of it and it will be a two form, and those are exactly the transformations of supergravity fields. We know that it's a general covariant theory, so we better have these infinitesimal diffeomorphisms, but we also have this gauge transformation of two form. And if we put these together and define a Dorfman derivative, which basically just takes these two facts together and places them in one object, we can define a Courant bracket, and it will be a natural generalization of what we have in usual geometry. One more generalization happens if we relax the fact that our generalized tangent bundle is globally of this form. We can actually just take this as a local prescription and then twist it by two form in different patches. that's a usual way we do with vector bundles. We say that when we go from one patch to the other, we multiply by some transition metrics, and here we can do similar thing. We identify things on patches with extra action of B field. So if we do this, we get out of the space of direct sums of Tm and T star m, but we still can define these more general structures, which are called current algebraics, and we still keep some information about this local structure in terms of this exact sequence. So we still require that the sequence is exact, meaning that each two maps composed after each other are 0. This map is of the main importance. It's called anchor map, and if we put these data on it, the commutator and the natural pairing, as I described before, and the anchor map, that constitutes a current algebraic. Why is this generalization good? Because we can express what the Drinfeld double is in the language of generalized geometry, and it's actually a current algebraic over a point. So same data, just no space-time dependence down there in a base. So and so that fits in our description nicely. Okay, so there's another generalization now, and that is what happens when we go from generalized geometry to exceptional geometry. Generalized geometry was a nice description of supergravity. Exceptional geometry is useful for M-theory description. So here I wrote a dictionary again. So it gets a little more complicated, but it's not too bad yet. Tm and T star m, the generalized tangent bundle gets promoted to some other object, which now depends on dimension, and it still has this Tm part, but then there are some higher forms, and as I'm saying, there will be more and more of them as we go up in dimension of M. Here was kind of unified throughout the dimension of the base. The structure group is the most surprising thing. Here it was the ODD for the reason of having the canonical pairing, but here it comes as a total surprise that we get these exceptional groups as a structure group. H, the generalized metric doesn't have really an analog on the exceptional geometry side. The reason being that we don't have a quadratic invariant for ED group, so we can't really compose the field binds in a quadratic invariant object as we do in ODD or in general relativity. However, we can work with the field binds easily, and really here the H was really corresponding to reduction of the structure group to OD cross OD. And we can similarly describe what the analog of generalized metric data is at the exceptional geometry side. Dorfman derivative and current bracket extends naturally. Also, I won't explain now. I have an example later. And oh yeah, the twisting by H form. Sorry, there's too many H's. This is not curl H, but H3 form. We can twist now with other fluxes, which corresponds to forms appearing in theory. And it's more complicated, but we can also do this local patching and describe something like a Leibniz algebraic. Okay.
Sorry, can I ask a question real quick?
Sure.
Oh, go ahead, David. Yeah.
Oh, sorry.
Go ahead.
So this exceptional. So if you scroll back up to this kind of these two columns here. So the right hand side, you're saying that these are kind of the objects that arise generalizing the generalized geometry case for supergravity. So if I truncate the right hand side of the table kind of to the supergravity sector of M theory? Is there kind of a, like, am I misunderstanding something? Is that the right hand side is somehow including a bunch of stuff that's beyond supergravity and M theory?
Oh,
or...
I see. No, yeah, there's a clear understanding of yeah, as you're saying, the M theory once put on a circle, it should be equivalent to a supergravity, right? And so that should be somehow reflected in these two generalized geometry descriptions. And indeed, there's a way to do the dimensional reduction. The problem is that here I haven't really I've been lying a little bit and didn't really fill in all the gaps there. Aside of having these degrees of freedom G and B, there's this whole RR sector.
Yes.
Yeah. In 2A and 2B theory, and the thing is that that is not so this constitutes a vectorial representation of ODD. To describe RR forms, you need to add the spinorial representation of ODD, and then if you start reducing and decomposing dimensionally this exceptional tangent space, you'll see that you'll get the factors in this vectorial part and also in this spinorial representation of ODD, and you indeed recovers the usual degrees of freedom of generalized geometry with the RR form sector. Is that answering the question?
Yeah, that's great. Thanks.
Yes, so sorry. Yeah, the RR forms, yeah, they are more complicated. They need to be added in slightly complicated fashion. So I dropped that out from my presentation. But that's another thing which is nice about exceptional geometry, that you really only have these vectorial representations of ED and everything's in there. All the RR forms will come out of the dimensional reduction. You're paying for it for slightly ugly description, but that's life. Okay, so I wrote down this table for different dimensions and what these EN groups are. It might look like a mess, but if you like Dinkin diagrams, it really, I wrote this Dinkin diagram for E6. You can see that if you start removing dots, so I'm starting here, and if I remove one dot, you see that I get an ED series, and indeed I have the spin 5, 5 here. If I remove another dot, I get an EA series, so I get SL5. If I remove another dot, now I'm removing this one, I get SL3, SL2, and so there's some pattern to this table. And okay, so just to give an example now, I'll show you what those structures are in ODD case. Well, I called ON case for some reason here. So the pairing is, as I said before, just the natural thing you would do with vector and form. You just contract them in a way you can and make it symmetric. The Dorfman derivative is this. You act with the x part. You just do the usual Lie derivative, but when you're acting with a form, you take a d of it and you substitute in y. So you get a one form again. It naturally lives in T star. There's a caveat to the Dorfman. Sorry, not Dorfman. Dorfman Lie derivative, and that is that it's not symmetric as the Lie derivative was. But if you think about it, it's not really needed. What you really need is Jacobi identity, and that's still satisfied for this Lie derivative. So things are okay. And lastly, the ODD. If you look at what are the individual parts of ODD, there's general linear part at the diagonal. Those constitute the rotations of your frames in tangent space and cotangent space. So you actually rotate in a covariant contravariant way so that you don't spoil the canonical pairing. But you also have these two forms and two vectors which act on your generalized tangent bundle in the following way. So you would transform x and w with the diagonal parts, and then you would substitute x in two form. And I guess I didn't add the last part. And in beta, there you would put in the omega. So things work nicely. Now I'll give you an example. I guess my time's almost up, but how much time do I have? I'm almost towards the end, actually.
We usually go until about the top of the hour, yeah, with questions included. So
okay,
you can keep going through the slides. It's no problem. So got 15 minutes.
Okay. Good. I think I don't even need that much time. So SL5 example is particularly nice because it's still it's already the exceptional geometry, but still some tangible group SL5, not some weird ED. And so it corresponds to space being 4-dimensional. So I'll give you some algebra workout here. If TM is 4-dimensional, we see that this second wedge power is 6-dimensional. So this exceptional tangent bundle is 10-dimensional. And GL4 part, which is just the geometric subgroup, acts on it in a natural way on these two factors independently. But then if we accompany this GL4 by 3 forms and 3 vectors, we can act in a similar way as we did in ODD, meaning that we contract what we can contract. So if we have vector in 2 form, we can put the vector in 3 form and get 2 form and add it to the result. And likewise with the 3 vector, we can contract that with 2 form, which will stay in the exceptional tangent bundle. And this will, all these together, 3 forms and 3 vectors and GL4 will constitute in somewhat non-trivial way SL5 group. It really needs to be, there's no easy way around it. At least I don't know easy way around it. You really need to sit down and calculate the commutation relations of these actions. But at least that would take a long time, and at least to give you some reassurance, here you see that if SL5 has dimension 24, 24 decomposes as 4 plus 4 plus 16, and 16 is dimension of GL4, the geometric subgroup, and then these two are exactly 4-dimensional. So it's not a proof, but you see that it might work out, and indeed it works out. And then once you see that this SL5 has an action on exceptional tangent bundle, you also recover that it's actually second wedge power of the fundamental representation of SL5. So these are quite surprising things occurring in exceptional geometry. There's a caveat in to the whole story, which kind of renders things complicated, and that is that we, as I mentioned before, there's no canonical pairing, there's no quadratic invariant in those ED groups, but we have something along those lines. We have this product. We can take 2 generalized vectors or exceptional vectors and contract them in a fashion in the only possible way we can do, as in putting this x in B and putting this y in alpha, and we end up in D star, which I called here n. This n also extends for higher dimensions, but this is for this n equal 4-dimensional model. And then we can really see that this SL5 corresponds to the transformations of this E, which are equivariant with respect to this product in quotation marks, because it doesn't go to E but to some other bundle.
So these why I'm studying these exceptional algebraics is exceptional tangent bundles and exceptional geometries is the reason is that as I described before, there's this blueprint for general T duality, and that is the Drinfeld double, where we can define our model, and then by choosing these projections, we get T-dual descriptions there. However, what's lacking on the M-theory side is a good definition of something what's a Drinfeld algebraic in M-theory, and that I like to call Leibniz algebraic. I think people usually use that description. There's not really a good geometric description of that object, we think with my amazing collaborators, Mark Bogdan and Fritzo Balach, we think that we kind of understand some more geometric description and definition in n smaller than 7, exploiting this this projection down to auxiliary bundle n, and studying isometries which are equivariant with respect to this projection. Then we can define in more geometric terms what these Leibniz algebraics are, and by so doing we can probably learn some more interesting things about some general things about Udality in M theory. Going over dimension 7, that's unclear, at least to us. However, we have people in general have many examples of these Leibniz algebraics. It's not like it would be totally unknown what these objects are. And for instance, there we have a nice example where we can manifest the so-called spherical T-duality, which I put the T-duality in quotation marks because it's really U-duality at the level of M theory. But we think that we know the Leibniz algebraic description of this spherical T-duality. We can also describe some interesting subclass of Lie algebraics, which are actually Lie algebras, and that simplifies some things drastically. But the problems of the biggest problem with the Leibniz algebraics is that in general people really just give you definition in terms of the structure constants. These structure constants are not even antisymmetric, and first of all, you don't really know what's the global structure of these objects. You can't really integrate these algebras to some group kind of objects, so that we don't really understand. And as I'm saying, the general definition is still lacking, and that's what I'm mostly focusing on now. Okay, I guess I said pretty much everything, so we can maybe stop and move to questions if there are any.
Okay, great. So I know it's hard to applause over Zoom, but I think most people are. I really appreciate that talk. I learned a lot. So let's see if there are any questions, maybe from people who haven't asked questions
Should I
yet.
turn off the sharing? Maybe
it's up to you. You might, maybe someone will have a question about a specific slide. So
okay, yeah. Okay, then I'll
I have a question.
Mm-hmm.
Hey, Ondrej, great job.
Hi.
On this presentation. I want to, my question is there any connection between, so for Lie algebras, there is this dual description, the Marais-Cartan description.
Yes.
Yes, and then you can using one forms, and then one can generalize that, and then you have what's called the differential free algebras. I was wondering if there's any connection between differential free algebras, which are also used in supergravity, and exceptional geometries.
So yeah, I'm not sure. So you can also have a dual description of this object. Just along the same lines, you can look at the dual basis and define some exterior derivative on those. And actually, there's whole class of examples where you can construct Leibniz algebraics out of group. You have a group, and on that, if you construct this exceptional tangent bundle on G and furnish it with Drinfeld, sorry, not Drinfeld, I always mix up Drinfeld and Dorfman. With Dorfman Lie derivative, you get a nice example for every group of the Leibniz algebraic. And if you restrict yourself on left invariant forms. And to your question, so it seems, at least in those low dimensional examples, that you don't need those higher structures. That it seems like you just really need this Lie derivative or bracket pairing two objects and giving you one, or in dual description from one object getting two. But there's this whole literature on tensor hierarchies by Hom and collaborators, which I'm not really, I haven't studied in depth, and maybe so they see some L infinity structures behind these Leibniz algebraics, and so maybe there's something there, because L infinity algebras, they have these higher products. Maybe that's where things get similar to what you're asking, but that's all I know about that.
Okay, thank you. And if I may, a very short technical question. So if I remember, a characteristic of the Courant bracket is that Jacobi identity is not an identity, it's up to gauge transformations. Is that correct?
Up to gauge.
So you have the Jacobinator, which is not zero, it's a total derivative.
Right. Yeah, that's true.
Right.
Yeah.
So the question is, the extended version of that, the exceptional version of that, of the Courant, I don't know, how did you call that? Has a similar behavior?
Yes, unfortunately. Yeah. It's always this trade-off. Like you have a Dorfman-Lie derivative and you have Courant bracket. They are related basically, this object satisfied the Jacobi identity, but it wasn't antisymmetric. If you antisymmetrize, well, you obviously made it antisymmetric into a bracket, but that one doesn't satisfy obeys Jacobi identity. But it's not really a problem. Really, what you want is,
that's fine. Yeah.
What you want is it would be a problem if this Dorfman-Lie derivative wouldn't satisfy Jacobi identity. But that thing does, and that's why this is spoiled when you go one step further into double field theory or exceptional field theory, where you see that this doesn't satisfy Jacobi identity, but it's up to something what if you enforce the sectional condition, it vanishes. So this is okay. Yeah.
Yeah. Great. Thank you.
Can I ask real quick about so the kind of original example you started with was a very simple, just kind of integrate in a gauge field. So you integrate in some extra. There's kind of a simple kind of path integral manipulations to get these the two kind of dual actions, for example. And so I mean, yeah, those kind of simple path integral manipulations by integrating in some gauge field,
right,
and then integrating things out in a different order. That doesn't work when you try to generalize to these non-abelian scenarios, or
yeah, right. That's true. Yeah, I didn't get into that. What happens if you're in non-abelian situation is that if you go down here, usually you can't go up in your parent action because you lose some symmetries along the way.
The program you've been talking about kind of seems to be a way to kind of work with these more general dualities without these kind of explicit, where you don't have these explicit kind of path integral tricks to at least guide your intuition.
Right. Yeah. Yes.
And so I was just kind of wondering, there's been a lot of these like webs of dualities of field theories between fermions, or these kind of bosonized duality webs in, say, 2+1 dimensional QFTs. They all kind of run along the lines of, okay, I can imagine integrating in some gauge fields and playing some game to integrate something else out and end up at some different theory. I was just wondering if you happen to know of any kind of applications of these kinds of technologies for, say, these 2+1 dimensional dualities.
Oh, I see. Off the top of my head, no, but yeah, I don't know. As you're saying, I guess it's the similar story to these integrating outs and gaugings. The problem is with as you're saying, even within string theory, this description is not valid all the way through in those generalized situations. And so you should really you should really abandon that gauging procedure and go into the train-fault double description. Maybe in that sense, in this in these dualities here, you're talking about, maybe there's some parent action also, like some formulation at the train-fault double kind of level, and then going down in one or the other direction, you can recover the original models. But here I'm only speculating. I don't really know.
Okay,
So it might be an interesting question to entertain.
I have a quick question, since I'm not super familiar with doing research or working in this field. So when you're building these different sorts of technologies or tools to find these dualities, to understand the geometry of the problems in different dimensions, is the goal just to understand better the structure of the original model, or is it to actually have a new tool that you can use to find solutions that couldn't be solved previously without knowing about these symmetries that are hidden?
So there's several things which are interesting. So first of all, as you're saying, it's a solution generating technique, and pretty interesting one, because you have some nonlinear equations of motion of supergravity or M theory, and you get one solution, you do this mumbo jumbo with the degrees of freedom, and off you get the some other solution. So that's quite remarkable. And if you especially if you go to these higher generalizations, well, they don't really solve original supergravity equations, but something called generalized. Everything's generalized, or generalized supergravity equations. But still, it's a solution generating technique. So it's interesting for that reason. Another thing, what's interesting is that these dualities, they can take you from some perturbative descriptions of string theory or M theory to other parts of the moduli space. So by having these dualities at your disposal, you can map the moduli space of the whole theory better, and maybe learn something from non-perturbative part of the moduli space. And I guess so this was purely classical, but some or all of these some of these dualities also hold at the quantum level of the field theory. So that's a whole another line of research when people are interested in as to whether these differently generalized dualities get promoted to fully quantum symmetries of string theory. Yeah, but mostly, I guess generating technique is one thing, and another thing is that it helps you look in other parts of the moduli space of your theory, which proved to be useful in other situations, like maybe that, and the S duality was crucial duality in like Seiberg and Witten study of n equal to super-Yang mills, because it again is a theory. It's again a duality which gets you from weak coupling description to strong coupling description, and you can learn something about more global questions of your theory.
So basically, like you can do a perturbative solution, and then you can, using these hidden symmetries, you can extend it to some part of the phase space that's non-perturbative, and you can learn something about the model. Okay, interesting.
Mm-hmm.
Okay, so if there are no more kind of standard Q&A like questions, I think we'll just say thank you one more time for Ondrej, but some of us are gonna stick around and have an extended discussion in terms of, kind of crazy research ideas or possible collaborations. So thanks again, Ondrej.
Thank you.